Some people think that this is a real motor. Well, maybe some kind of it is, but actually this is a little baby. Now this is a real motor. I'm gonna use it to drive my spindle in my new CNC lathe project. It fires 2,500 rounds per minute and it's got a lot of torque. Compared to the small brother, it's got 3.8 kilowatt of power and about 15 Newton meter of torque, which should be sufficient for all the work I like to do on my lathe. It can be controlled in analog mode, in positioning mode, in torque mode, and it can support also both the speed and positioning mode, which can be applied to a lathe. For example, it would work similar to a fourth axis of a milling machine. I'll try later to set it up like that and to have the possibility to change from one to the second mode from the operator panel. Regarding this motor, the servo, we've got the power input. It's got also a mechanical brake with this port making it possible to control. It is controlled by 24 volt DC, and the brake takes here the space behind the coils of the motor, and here on the end we have the encoder, also with quite some pins to exchange the data between the servo driver and the servo motor.
Quick correction. It doesn't exchange data, it just sends information to the driver.
This motor is powered by a 3-phase voltage, 380 volts, and it's got a quite big servo driver. This driver is also supplied with 3-phase 380 volts. It's quite similar to the drivers of the smaller motors, but it's much bigger. It consumes much more power, so it needs much more efficient cooling. The radiator is much bigger as on the smaller one. As some of you maybe saw already, that I'm going to use the CNC drive controller for my machine. It's going to work with the servo motor we are talking about today. This controller has got 2 analog outputs and 2 analog inputs. One of the analog outputs will control actually this motor through the servo driver. The controller has the analog outputs here on this port. It's a IDC 16 port. And to utilize it, we need a terminal block to take the signal out of these pins. For this purpose, I bought such terminal block. We just have to connect our servo driver, and after connecting the CNC controller with this board, we've got all covered.
In order to use the analog output, you want to check PWM spindle. You can set also the PWM frequency, but usually the 200 Hz is okay. And you can also set the range of the PWM duty cycle, which will directly affect the output voltage range. The M3 and M4 command pins and ports have to be set over here. These are the outputs which are activated after turning on the spindle clockwise or counterclockwise. Here is the minimum and the maximum speed of the spindle. Also there is the spindle acceleration time in seconds. Here we choose the analog output number where we want our spindle speed signal. I will type 1, so I will have the 0 to 10 volts signal on the analog output number 1. Hitting spindle clockwise and the M3 output LED fires up.
Set now in UCCNC the half of the maximum RPM on the spindle, which was configured. Halfway of 10 volts should be 5 volts, which is now measured on the output on this terminal block. Third from this side and the second from here is the output voltage of the first analog output. The same should be here and here. Yep. And now when I add some speed in the software, it should rise up to 10 volts. Yep, that's happening. And this is the maximum readout. Now in the opposite side, when I turn it down, it goes down to about 0.5, and this is the minimum we've earlier set on the spindle tab in the settings. Now if we would like to use the second output, we would have some kind of voltage between ground, which is here, and here would be the second voltage.
The encoder, simple connection. The motor coils cable, simple connection too. The power supply cable, simple stuff. This is the control signals cable, and by default it's got much less wires than it has pins in this connector, and to wire every pin we need we will have to break apart this connector and solder into some other pins we will need beside those which are already ready. Yeah, so let's do it. 2 words about which pins I'm going to use. For the analog input, I'm going to use the pins 26, 10 and 11, keeping in mind that if I'm going to use from 0 to 10 volts, then the pin number 10 and number 11 are going to be tied together. Next, in the close future, I will be in need of more digital inputs than the amount that is available, so I'm going to solder some more of them. Next, the outputs. The brake output is already soldered. Regarding outputs, I will use what is available now. The pulse and dir signals are also available already too. Actually, for speed control, those are not needed, but in the future I'm going to switch between the position and speed mode, so I will use those too. And the encoder signal output. Today I'm going to solder some wires there too, because I think I could use those to have the feedback from the spindle to my CNC controller, and I won't need the external encoder, but we'll see. This is not the topic for today.
Nice.
And the motor brake. Here's the things get a little bit complicated. So how the mechanical braking system works. Firstly, the motor gets the enable signal. After that there's a delay, which can be set, for example a half a second, and it activates the brake output. There is a relay needed, and the coil of the relay has to be connected to the output of the servo driver. Now the relay activates its contact, which is wired to a power supply, which is then connected to the mechanical brake coil, and the coil activates the brake. Being more precise, it actually turns it off, so the shaft is not braked. Also, in the manual we see a surge absorber, which should protect the contacts of the relay and the power supply, and the directional diode to protect the output of the servo driver. Actually, that shouldn't be complicated, but you will see later.
This is a relay.
some switches for digital input simulation. Another switch for enable signal simulation. And here we have it, everything ready to burn the brake.
Yes, I managed to destroy the brake. Yep. I have to confess that before I started to record everything, I managed to damage the brake. That was horrible. Really, this AC servo motor cost me like, I don't know, like $700, and that was really bad. But quite frankly, I have a friend that knows how to repair motors. I sent that motor to him and he was able to repair that. I was really scared. You will ask, what happened? I'm going to tell you. In order to rotate the shaft, there need to be supplied 24 volts over here to the coil of the brake, and I did exactly what I showed you before, but there was one problem. This was the problem. This is a new relay that damaged my motor. I was quite sure that this relay, well, it was new, so I guess it should work. And yeah, it was my mistake. I didn't check if the contacts are working. I powered the coil of the relay and I saw that the contacts are moving, so I assumed that it works. But it didn't work. The contacts were moving here, but not quite enough. And while I was really sure that I had delivered here 24 volts through the contacts of this relay, well, actually I didn't. I tried to run this motor on like 100 RPM. It worked. Later on 200 RPM, it worked too. This brake is supposed to be used to hold the shaft when the motor is not energized, but when it is energized, this brake has less holding torque than the motor itself. So the motor was still able to rotate, although this brake was braked. And you will ask, what happened inside? And I'm going to tell you that when I turned up the RPM on the motor to about 2000 RPM, well, I was quite sure that I did everything properly, but there was a moment when I felt the smell of a burnt brake. I instantly powered off the motor, and that probably was the second mistake, because when it cooled down, it welded together. I wasn't able to move the shaft at all. So please remember, don't do my mistake and make sure that you are providing voltage to the brake before you start actually using your motor. So for the rest of our tests, I was not brave enough to use a relay on the mechanical brake, and I'm going to provide for the brake the 24 volts all the time, so I'm sure that the shaft can actually move and I won't be able to damage the brake anymore. At least today. So for today we have the signal enable button, and we have also wired two other digital inputs, and one of them will be used to change the direction of the rotating shaft.
And the second one will be used in the future.
So summarizing, we have the basic spindle control all covered. There were some questions about if you can use the encoder of such motor to use it for your spindle feedback, and I have already tried it, and my conclusion is that it depends on the servo driver you have. This particular one doesn't have the possibility. Well, it has the possibility to output the encoder feedback signal, but it has such a big frequency that our controller is not able to keep up with the frequency we have here on the output. And from what I know, this servo driver is not able to divide the frequency of the pulses we get on the output. So we actually get on the output the same amount of pulses which this encoder physically has on its output. That's 2,500 pulses per revolution, which transfers to about 10,000 counts per one revolution, which is really high. As far for what I know, the UC300ETH can keep up with signals up to about 50 kHz, which is, well, not enough to reach such fast signals. But I think I have an idea how to do it. So if I success, I will make a video about how to do it. But I said it depends on the servo driver, and that's probably true because some other servo drivers have the possibility to divide the frequency of the encoder output, and that leads to a slower feedback signal. Such feedback signals are usually used for threading, for tapping, for synchronizing the axis with the spindle, and usually for that we don't need such a high resolution of that signal. So when you have a servo driver which has the possibility to divide the frequency of the encoder output signal, then you should be probably able to use the encoder of the servo driver as your spindle feedback.
And if you want me to break more expensive stuff, feel free to subscribe or maybe even become a patron. Thanks for watching and see you next time.